Hello and welcome to the channel. Today we're diving into some of the most practical and widely used algorithms in computer science, traversals and optimization algorithms. Let's begin with one of the most famous problems in graph theory, finding the shortest path between vertices. Imagine you're using a GPS navigation system. This is exactly the type of problem it solves millions of times every day. Problem statement analysis. The formal problem statement is as follows. Given a weighted graph G equals V, E, where V represents our vertices and E represents our edges, with non-negative edge weights, we want to find the shortest path, that is, the path with minimum total weight, from a source node to every other node in the graph. Notice the critical constraint here, non-negative weights. This is essential for Dijkstra's algorithm to work correctly. Dijkstra's algorithm, developed by Dutch computer scientist Edgar Dijkstra in 1956, is used everywhere: GPS systems, network routing protocols, social network analysis, and even in video games for pathfinding AI. Let me walk you through the intuition before we dive into the steps. Dijkstra's algorithm works on a greedy principle. It always makes the locally optimal choice. We maintain tentative distances to all vertices and progressively relax these distances as we discover shorter paths. Step 1. We initialize the distance to all nodes as infinity, except our source node S, which we set to 0. This makes sense. We're at the source, so the distance to reach ourselves is 0. Step 2. We maintain a minute priority queue of unvisited nodes, ordered by their current shortest distance. This data structure is crucial for efficiency. Step 3. We repeatedly pick the node with minimum tentative distance. This is the greedy choice. We're betting that we've found the shortest path to this node. Step 4. For each neighbor of our selected node, we perform what's called relaxation. If the path through our current node offers a shorter distance to the neighbor, we update the neighbor's distance. Step 5. We mark our current node as visited and repeat until all nodes are processed. Let's trace through the example graph shown. We have vertices A, B, C, and D. The edges are A to B with weight 4, A to C with weight 1, B to D with weight 2, and C to D with weight 5. Starting from source A. Initially, A equals 0, B equals infinity, C equals infinity, D equals infinity. Process A. Update B to 4 via AB, C to 1 via AC. Process C. Smallest unvisited update D to 6 via ACD. Total 1 plus 5 is equal to 6. Process B. Update D to 6 via ABD. Total 4 plus 2 is equal to 6. No improvement. Process D. Complete. Final distances. A equals 0, B equals 4, C equals 1, D equals 6. The time complexity depends on our implementation. With a simple array, O, V squared, because we scan all vertices to find the minimum each time. With a binary heap or priority queue, O of V plus E times log V, because each vertex is extracted once, V log V, and each edge is relaxed once, E log V. The heap implementation is preferred for sparse graphs where E is much smaller than V squared. Now let's move to another fundamental optimization problem, finding minimum spanning trees. This concept is crucial in network design, from laying fiber optic cables to designing circuit boards. First, let's clarify what we mean by a spanning tree. A spanning tree of a graph is a subgraph that satisfies three conditions. It includes all vertices from the original graph. It remains connected. There's a path between any two vertices. It contains NO cycles. Adding any edge would create a cycle. The minimum in minimum spanning tree refers to having the smallest possible total edge weight among all possible spanning trees. Think about these scenarios. You're a telecom company wanting to connect all cities with fiber cables using minimum total cable length. Or you're designing a computer network where you want to ensure all computers can communicate while minimizing connection costs. These are MSD problems. Kruskal's algorithm embodies the greedy approach beautifully. The idea is elegantly simple. Always pick the smallest weight edge that doesn't create a cycle. Talking about algorithm steps now. Step 1. Sort all edges in the graph by their weights in ascending order. This pre-processing step is crucial. Step 2. Initialize a disjoint set data structure, also called union find. This efficiently tracks which vertices belong to the same connected component. Step 3. Iterate through sorted edges. For each edge, check if adding it would create a cycle by testing if its endpoints are already in the same connected component. Step 4. If no cycle is formed, include this edge in our MSD and union the components. Step 5. Stop when we have exactly V1 edges, where V is the number of vertices. Why V1 edges? Because any tree with V vertices must have exactly V1 edges. This is a fundamental property of trees. Time complexity. The bottleneck is sorting edges, giving us O, E log E. The union find operations are nearly constant time with path compression and union by rank. While Kruskal's works with edges globally, Prim's algorithm takes a vertex-centric approach. We grow our MSD one vertex at a time. Algorithm logic. Step 1. Start from any arbitrary vertex. The choice doesn't affect the final MSD weight. Step 2. Maintain a list of edges that connect our current MSD to vertices not yet included. Step 3. Among these frontier edges, always pick the one with minimum weight. Step 4. Add the selected edge and its new vertex to our MSD. Step 5. Update our frontier edges and repeat until all vertices are included. Time complexity. Similar to Dijkstra's O, V squared, with simple implementation, or O, V plus E, log V, with a priority queue. Consider our triangle graph. A connects to B with weight 1, A connects to C with weight 4, and B connects to C with weight 3. Kruskal's approach. Sort edges, 1, 3, 4. Pick AB, weight 1, then BC, weight 3. Total, 4. Prim's approach starting from A, choose AB, weight 1, then from AB, choose BC, weight 3. Same total, 4. Both algorithms guarantee the same MSD weight, though the specific edges chosen might differ when weights are tied. Let's now explore the fundamental graph traversal algorithms, starting with depth-first search. These algorithms are the building blocks for countless other graph algorithms you'll encounter. Imagine you're exploring a maze. Depth-first search is like the strategy of always taking the first unexplored path you encounter and following it as far as possible before backtracking. It's the go deep, then backtrack approach. DFS explores as far as possible along each branch before backtracking. It's naturally recursive in nature, which makes it elegant to implement and understand. The recursive DFS algorithm is beautifully simple. Let's trace through the tree structure shown. A is connected to B and C, while B is connected to D and E. Starting DFS from A. Visit A. Mark it visited. Explore A's first neighbor B. From B, explore B's first neighbor D. D has no unvisited neighbors, backtrack to B. From B, explore B's next neighbor E. E has no unvisited neighbors, backtrack to B, then to A. From A, explore A's next neighbor C. C has no unvisited neighbors, algorithm completes. The traversal order is A, B, D, E, C. Key properties of DFS. Memory efficient, uses O, V, space for the recursion stack in the worst case. Edge classification. DFS helps classify edges into tree edges, back edges, forward edges, and cross edges. Cycle detection. Back edges indicate cycles in the graph. Topological ordering. DFS is fundamental for topological sorting in directed acyclic graphs. Time complexity analysis. DFS visits each vertex exactly once and examines each edge exactly once, or twice for undirected graphs, giving us O, V plus E, time complexity. This is optimal since we must visit every vertex and edge at least once for a complete traversal. Applications. DFS is used in pathfinding, cycle detection, topological sorting, strongly connected components, and maze-solving algorithms. Now let's contrast DFS with breadth-first search, which takes a completely different exploration strategy. If DFS is like exploring a maze by going as deep as possible, BFS is like spreading out from your starting point in all directions simultaneously. It's the explore all neighbors first approach. BFS explores all vertices at distance k from the source before exploring vertices at distance k plus 1. This level-by-level exploration has profound implications for shortest path finding in unweighted graphs. Unlike DFS, which uses recursion and thus a stack, BFS uses a queue data structure. Why a queue? The queue ensures first-in first-out processing, which guarantees we process vertices in order of their distance from the source. Tracing the same example. Using our tree, A connected to B and C, B connected to D and E. Starting BFS from A. Enqueue A, mark visited. Q, A. Dequeue A, enqueue its neighbors B and C Q, B, C. Dequeue B, enqueue its neighbors D and E Q, C, D, E. Dequeue C, no unvisited neighbors. Q, D, E. Dequeue D, no unvisited neighbors. Q, E. Dequeue E, no unvisited neighbors. Q is empty. Traversal order, A, B, C, D, E. BFS tree structure. Notice how BFS naturally creates levels. Level 0, A, distance 0 from source. Level 1, B, C, distance 1 from source. Level 2, D, E, distance 2 from source. In unweighted graphs, BFS guarantees that when we first visit a vertex, we've found the shortest path to it. This is because BFS explores vertices in order of increasing distance from the source. Time and space complexity. Time, O, V plus E, same as DFS. Space, O, V, for the queue in the worst case, when all vertices are at the same level. Applications. BFS is essential for shortest path in unweighted graphs, level-ordered tree traversals, finding connected components, and social network analysis, degrees of separation. Let's examine the tree structures created by our traversal algorithms and their practical applications. DFS creates a tree from the edges we traverse, but also classifies all graph edges into 4 types: tree edges, our traversal path; back edges, connecting to ancestors, these indicate cycles; forward edges, ancestor to descendant; and cross edges, all others. This classification makes DFS perfect for cycle detection. BFS trees explicitly show distance relationships through levels. Level 0 contains our source, Level 1 contains vertices at distance 1, Level 2 at distance 2, and so on. This level structure guarantees that BFS finds shortest paths in unweighted graphs. DFS trees are deep and narrow. They explore deeply before backtracking, making them ideal for cycle detection and topological sorting. BFS trees are wide and shallow with explicit level structure, perfect for shortest path queries in unweighted graphs. Use BFS when you need shortest paths in unweighted graphs. Use DFS when you need cycle detection, topological ordering, or deep exploration of graph structure. Connected components are one of the most intuitive concepts in graph theory, yet incredibly powerful in practice. A connected component is a maximal set of vertices where every pair is connected by some path. Think of them as separate islands. You can travel between any 2 points on the same island, but you can't reach other islands. In formal terms, connected graph has exactly one component, the whole graph. Disconnected graph has multiple components. Looking at our example, component 1, A, B, C, 3 vertices connected. Component 2, D, E, 2 vertices connected. Component 3, F, 1 isolated vertex. This graph has 3 connected components total. Algorithm to find components is beautifully simple. Why this works? Each DFS-BFS traversal visits exactly 1 connected component, no more, no less. Time complexity. O, V plus C. We visit each vertex and edge exactly once across all traversals. Key applications are in social networks, finding distinct communities. Network reliability, identifying which parts remain connected after failures. Data clustering, natural grouping without specifying cluster count. Biology, identifying functional protein modules. Let's now look at the time complexity of key graph algorithms. Depth-first search and breadth-first search both have a time complexity of order of V plus E, where V is the number of vertices and E is the number of edges. Dijkstra's algorithm, when implemented with a priority queue and an adjacency list, has a complexity of order of V plus E log V. Kruskal's algorithm has a time complexity of order of E log E due to the need to sort edges. It is most efficient on sparse graphs. Prim's algorithm has a time complexity of order of V squared when using an adjacency matrix. But when implemented using a binary heap with an adjacency list, it improves to V plus E log V, making it more suitable for dense graphs. This part is important. Take a moment to read it thoroughly. Once you understand the concept, solving questions becomes effortless. This shows how the complexities for Kruskal's and Prim's algorithm evolves in different cases. Use Kruskal's algorithm when the graph is sparse, meaning it has fewer edges compared to the number of vertices. Use Prim's algorithm for dense graphs where the number of edges is large. If the edges are already sorted, Kruskal's algorithm becomes even more efficient. Let's connect these algorithms to real-world impact. Connected components applications are in social media, community detection and network analysis. Infrastructure, identifying service outages and planning redundancy. Bioinformatics, finding protein interaction modules. Data science, natural clustering without predefined groups. MSD applications are in network design, minimum cost cable or road layouts. Circuit design, optimal connection patterns. Approximation algorithms, base for more complex optimizations. Image processing, segmentation and feature extraction. We've now covered the essential graph algorithms that power everything from GPS navigation to social media analytics. From shortest paths with Dijkstra's algorithm to network optimization with MSD techniques, and from basic traversals to connected component analysis, these algorithms form the backbone of countless real-world applications. The key insight is that algorithm choice depends not just on correctness, but on understanding your graph structure and performance requirements. That's a wrap. Thank you for watching this video. Don't forget to give it a like, share with your friends and subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.